Hello, everyone. My name is Rajesh Mishra. I'm an engineering lead on the GCE team doing control plane work. I'm joined here by my colleague, Vikas.
Hi, everyone. I am Vikas Yadav. I am an engineer on GCP, and I support the storage solution for GCE.
So what we plan to cover is how we design our control plane to be highly available. So let's get started. So before we get started, let's talk about control plane at a very high level. So we have an extremely simplified version from a customer standpoint. So what you see over here, what it takes to orchestrate an API that you submit against our control plane. So I've picked a canonical example of submitting an instance creation request. So that API, we orchestrate that API. That API has many, many steps to be performed. So I just listed some few of the steps. We need to check the permission. We need to check the org policy, quota, so on and so forth. Any one of these steps could fail. So, and you can imagine control plane with many projects, many resources that we manage, many APIs that we need to process. We need to process and remember where we are exactly, and so we can recover out of failures. And since this talk is about the availability, let's define what's an availability. So our SRE reliability workbook defines availability as an uptime of a software service. And the way we calculate our availability is by accumulating all the unavailable periods of downtime over some window of time. So as an example, 4 nines implies your service was unavailable over a 30-day for 4.3 minutes, and so on and so forth. There are a couple dimensions to availability for a GCE system. The VM uptime availability. This is nothing but your VMs are programmed, the network's being configured, your PD is configured, and all the other stuff has been programmed by the control plane, and your resources are now serving traffic, live traffic. That we call VM uptime availability. Just to draw some distinction, we have control plane availability, which is basically an on-demand control plane programming that happens via one of our REST APIs. And at a very high level, the control plane programming centers around 3 key resources: the VM, the virtual machines, the PDs, and any kind of network access you configure. And there are many more resources, of course, and I haven't listed them. So it's important to remember the distinction about these 2 availability things. The first one is live traffic serving paths. The second is control paths. We're so proud of the availability work we have done that we have a published SLA for VM uptime. So for VMs that leverage our multiple region, so for example, VMs placed in 2 or more zones in a region, or it could be split cross-region, one can expect an aggregate uptime availability of 4 nines. And this would be with no loss of external connectivity or access to persistent disk. Most importantly, this will be without any kind of downtime and will be transparent even if we carry out any kind of host maintenance. So if you have to carry out any kind of security patches, we'll do that transparently by live migrating your VMs. And in most cases, you won't notice that.
So in the previous slide, the security patches we are talking about is the underlying system on top of which the VMs run. And we do live migration when we are patching the host on which the VM runs.
So while I talked about the VM uptime availability, we don't have an SLA that we publish for our control plane. But the internal work we have done, we're very proud of what we have achieved. The designs that we have that we'll talk the rest of the presentation on our control plane availability. So as you guys know, sorry, before we get started, I need to introduce some key concepts before that are important in the VM that are important in our control plane. So as you guys know, we serve 17 regions globally. Each region can have multiple zones, at least 3 or more, and they're spread globally. Regions are connected to extremely fast network and highly available network. So any given region will have at least multiple redundant network paths, which is, as Brad Calder pointed out earlier this morning, it's a pretty key point of Google Cloud Platform. The rest of the presentation, we're going to talk through some of the design points that has worked really well as we work to offer a highly available control plane. And this is the system that offers all the API we serve. So I need to introduce some key building block foundations before we get started. So GCE resources, this is a GCE resource data model. Resources like VMs and disks are zonal resources. Subnetworks, static IPs, regional disks, these are shared resources, but they're shared across within a region. Global resources, and the most important ones are images, snapshots, and instance template. They're shared across globally by all the regions. So you can imagine this in a very object-oriented sense. You have a hierarchical access pattern. And we'll talk through this. We'll refer to this data model as we explain the kind of choices we made to build a highly available control plane. So Vikas, you should just jump in as...
Yeah, I want to spend some more time here. So we have a concept of resources which are available globally. So what that means is if you have an instance template which you want to use to launch VMs in multiple regions, you have to define it only once, and it will be available in your entire project across all the regions. You don't have to create separate template for different regions. So in some sense, this provides simplicity of management and single pane of control. And similarly, there are some resources which are region-specific, which are used by all the zones in the region. And they follow a natural pattern, like IP addresses, which are local to the region, which can be used within the zones in the region. And this natural hierarchy of sharding of the data model helps us achieve high availability, as we will talk about in the rest of the presentation.
So some of this will start to make a lot of sense as we dive deeper into the rest of the discussion. So we could have chosen a model, we could have chosen a design to have control plane served out of a single scope, have everything be global with a served out of global state database. But as we know, that's a single point of failure. This could work as an improvement over the previous design. So what you see is each individual scope, so all the scope data model that I talked about, resources that are in the individual scope, they're served out of the individual control planes.
Yeah.
However, in this case, we're sharing a database. That, again, is a single point of failure. One key point here that I talk about from a topology standpoint, we have a front end. We have our Google front end, which is nothing but a service router. And there is a second level of router we have, which I've called it here as API dispatcher. And all it does is it's a scope parser. So in our URL path, all our resources are scoped. So you could reference, let's say, a disk, and a disk, as we know, is a zonal scope. So based on the specific zonal scope that you're interested in, the right control plane will be involved here. It's important to also call out that there is only one singleton global scope, and we serve 17 regions, so there are 17 regional scopes. And likewise, there are, and I just made a very gross generalization, that there are 3 zones per region. So about 51 independent control planes serving resources within the scope. So this is the final design. This is what we have in production. This is what we use. We have independent control plane with their own independent databases.
So the theme here is, if you want availability, you need to minimize shared point of failures. So in the slide number 1, there's a single stack, which is not going to work for availability. Second slide, things are independent, but there is a shared database, which again reduces availability. Having independent control stacks increases the aggregate availability because there is no shared fate between those stacks. And that's what we have zeroed in on, that we are not going to have shared fate across different stacks and have multiple different stacks for different scopes.
Another key point that we felt was sharing. As we design our system, what about config? And what about updating all the scope control plane binaries? The model we have chosen is we do multi-day phased rollout. And this is largely to limit blast radius. So there are some config that needs to be rolled out globally across all the control planes that we serve. And we do this in a very staged fashion. We have circuit breakers along the way, and we do a lot of monitoring as we tier the rollout. So we watch rollout. We do zone by zone rollout. And based on the success, we will take it forward. And or some short period of time, the rollouts are completed. And then you get a new version of control plane, and if there are any config changes. We do a lot of upfront validation. We are pre-submit testing and staging testing. So that's our design point number 2. Let's spend some time on something that we've internally started to call Rule of 9. And what this simply stated, assume you're trying to provide a service called Service A, and it's serving a critical API. This could be your GCE system serving Create Instance API. And Service A is now is built on a lot of internal services we have. Identity as an example, and access check. So a lot of these underlying dependencies need to offer at least an availability that is higher than what I'm trying to provide to our customers. And you can imagine n layered of dependencies, and we'll go higher at every layer below. And that's the Rule of 9. So we followed this very diligently by inspecting all the dependencies across the board. So that's design point number 3. The subsequent discussion, since this talk is about distributed systems and control plane, serving control plane availability, let's spend a minute to talk about CAF Theorem. So CAF Theorem stated there are 3 key factors or 3 key design consideration points in any distributed system design. So distributed systems are partitioned by nature. So that's how much partition tolerance you need to build for your use cases. Availability and consistency are the other 2 parameters that you can play with. What CAF Theorem states that you can pick only 2 of these, and you're probably trading off on the 3rd one. And that's what, in the intersection of all 3, that's almost an impossible thing to build. So you could either end up with a system that is either consistent and available at the same time. That's typically all the old school single server model. Or more than often, in a distributed system, availability is extremely important, which has been the kind of choices that we made for a lot of our design. And we picked AP-based model. In some cases, you might have consistency and partition tolerance if it's a shared global object. And we'll talk about that subsequently. So here, what I have an example where we do some kind of lazy state reconciliation. So imagine there is a critical API being served out of your service, and there is a dependency layer below it. You could pick a choice where you fail close, and you need to reconcile the state synchronously. In a partitioned system, this can be tricky. And for some cases, we felt instead of improving availability, it was acceptable to just do a fail open.
Yeah, so one example I'll bring up here is in your application as well. If you have high availability for your API, but you have a dependency, which is not a critical dependency, and you can live with fail open semantics, then you don't have to force the rule of 9 on the dependency downstream. For example, let's say logging. You don't have to require logging have higher nines of availability. If you can reconcile, build a reconcile in your system, that if logging is not available, you still continue and reconcile later. So that's some of the pattern we have used for non-critical dependency, where we continue the operation, continue the top-level API available, and reconcile later.
So that's our design point number 4. Do a fail open and do lazy reconciliation. So this is in some ways, this is some sort of like an eventual reconciliation. Let's talk a bit about instance template. Remember, in our data model, I talked about instance template and snapshots are global resources. So what about them? Does that pose a problem for GCE system? Yeah. So I did a deep dive on instance template.
Yeah, the reason we want to talk about instance template is earlier we showed you that we have separate control stack for every scope, and there is a single global scope. So instance template are global resources which are served out of a single stack. So it's important for us to explain how we achieve high availability for instance template and snapshot. So Rajesh is going to talk about that.
So instance template is something that gets configured. So this is a typical workflow of an instance template. You create an instance template. It's a global resource. And typically, managed instance group depends on referencing an instance template, and which is then in turn used by VM creation within the managed instance group. So it's a global resource, and it creates a global dependency for something that is a regional API or a zonal API. This could be a problem. And so how does auto-scaling or auto-healing within the context of a managed instance group work? So by the way, there is a managed instance group. Folks are doing a presentation later today. They will talk a little bit in more detail about regional scaling, regional auto-scaling, and regional managed instance group. What's very key for both auto-scaling and auto-healing you need to be able to create instances and reference your template. So the solution we've arrived, we cache instance template in all regions. We actually do 2 levels of caching. The intuition that we operated on is that it was acceptable to go with eventual consistency via an AP-based model. So we just talked about CAP, and this is the AP model that we could successfully apply for instance template.
So the availability of instance template is high because we cache it. And what that means is if a single global scope or single global stack has a problem, the instance templates which are cached with the regions and zones, they're available for auto-scaling and auto-healing to work.
And there are more nuances to this, and I'm not talking about all the use cases. So there are nuances of you're trying to delete an instance template, so what then? And we can cover that if there's interest later in the presentation. OK, I built this twice. My apologies. So let's spend a minute on Snapshot. So Snapshots is another global resource. Snapshots are taken on your disk, which is a zonal resource. So, however, there's something that we did that we never exposed to customers. The underlying snapshot has always been a multi-regional concept, except the snapshot resource itself, the metadata, has been a global resource. It stored the GCS buckets where the physical raw snapshots are stored. It's a multi-regional concept.
Yeah, so this is important. If you have a zonal disk and you take a snapshot, you don't have to worry about that zone not being available and you're not being able to access your snapshot. So the metadata for snapshot is global, and it's available via eventual consistency in all the other regions. The GCS bucket where the snapshot data is stored, that is multi-regional, and that provides higher availability for the actual snapshot content and high availability for the snapshot metadata. So you can imagine a scenario where your zonal snapshot, once the zone has trouble, you can use the snapshot and utilize that in some other zone.
So Vikas already covered this. There's another thing that we announced at GCP Next. We're gonna, or which has been in alpha, in an alpha mode for some of our customers. We're now going to expose the snapshot locality. So as I told you, the underlying multi-regional locality will get exposed. There's a new parameter we're exposing called storage locations. So you'll be able to learn where your physical snapshots are getting stored. Additionally, we're going to allow you providing choices for where your snapshot will get stored. So this can be done on your request body by specifying the specific multi-regional place where you need to get your snapshot stored, if you don't want us to choose. Or you could specify specific regions. So you could have your source disk in US, in any one of the zonal US zones, and you could pick your regional destination to be in Europe. This is what it looks like. That's the parameter. So I've given 2 examples. Storage locations with just one location, or you pick a multi-regional thing. So the multi-regional is a GCS construct. EU simply implies it's one of the EU regions. And you could, as I explained in the previous thing, we will tell you what are the specific multi-regional, what's the specific multi-regional places where we place the snapshot on. So the design point in both snapshot and instance template that has worked for us is eventual consistency and UX. So let's take a moment and talk about the UX. The choice we could have taken is we could have converted this into a regional resource. We could have deprecated our existing global resource and offered regional equivalents of those. And we felt this is a good user convenience to a lot of customers. Because oftentimes you try to create a snapshot and make them available in multiple regions. And you're going to end up doing the work yourself. So we're just saving the burden by taking on a lot of the complexity as part of the GCE system. So the UX was a key point. So we didn't want to trade off on some of the user convenience. Meanwhile, we could achieve all the high availability characteristics by providing eventual consistency by caching those resources in each one of the regions. So that's our design point number 5. So this is a recap of all the 5 design points we covered. And above all, and most importantly, and it's an operational point, at Google, most services, we carry out something we call DIRT. DIRT is disaster recovery. And we simulate failures. We simulate region unavailability. We simulate latency. And we want to make sure our APIs are well behaving across all those failures that could happen in real world.
And this DIRT exercise is invisible to the customer. We do it internally, it's planned, and we prepare for it. And we want to see the system behavior when disaster recovery is going on. And this does not impact any of the external VMs or external client traffic.
So far we've discussed our data model and the fact that our resources are either our scope resources, so either they're zonal, regional, or global. So, and you could use control plane to provision your resources. And you could do this on demand in real time as you're serving traffic, or you could pre-provision. So let's apply some lessons. So there are 2 ways to approach this when it comes to serving real-time traffic for critical operations. So let's imagine you built a service, you built a GCE application that serves 1,000 QPS. And let's say you did one of those good best design practices that we advise on GCE, and you leverage 2 zones. In this case, US East 1A and US East 1B. In my contrived example, each VM has been tested to serve 100 QPS, and they've been tested for that. So you have 5 VMs on the either side on 2 zones, isolated, served by isolated control planes. And even the VMs are completely isolated because they're in 2 different serving paths. Imagine you lose one of the zones. You're going to double the traffic on US East 1B. This may be not desirable because you tested your service for 100 QPS. So the choices you have, you would go on demand, ask for 5 more resources or 5 more VMs. There is a possibility you may not get 5 VMs because we may stock out. Maybe US West 1A is experiencing a zone-wide failure, and every other customer is trying to do the same thing. That could be problematic. So you could pre-provision. In pre-provisioning, you will pre-provision 5 more instances. So here you end up with 10 instances each. And in reality, the traffic will look like this in a steady state. So you're serving half what you tested for, and that may be a safe place to be. And in the event you lose a zone, you would be safely able to serve twice the amount of traffic because that's what you tested for. So let's recap what we learned. So if you pre-provision, you're done with the control plane, configuring your VMs, the disks, and all the network programming that goes with it. And then at that point, your VM is serving live traffic. And we have a published SLA for that. And that works out really well. So the pros are, this pattern is predictable. It's simple. On the downside, it costs a little bit more. And in a steady state, or in the average case, your system's a little less utilized. In the on-demand, you put the control plane on the critical path. So here, you save on utilization, and that's an advantage that could work out for some of your use cases. But this is unpredictable. If it's a Black Friday, you may not get your instances.
So the on-demand model is where if you run into a problem in one of your zones, you try to allocate in other zones equal number of VMs which you need. And what Rajesh is pointing out, it's not a guaranteed unless they're reserved or provisioned that you need X amount of VMs, you'll get X amount of VM. It could be a stockout situation. It could be a thundering herd problem that the zone you want, that's overcapacity, and nobody can get extra VMs.
So that concludes our presentations.